Go.
Nice. For our physics project, we had mechanical energy, which is defined as the ability to do work. And in order to calculate this, we dropped a ball at different heights and calculated both the potential and kinetic energy. You can see our beautiful drawing right here.
The definition of mechanical energy is the energy of motion or a potential for motion on a macroscopic scale exists as kinetic energy of motion and potential energy based on position of an object in a system. Energy required by the objects upon which work is done. First of all, we put Melissa's arm at different heights and measured its height in centimeters and then divided it by 10 to convert it to meters. So we did it at 1.8 meters, 3.8 meters, 5.8 meters, 7.8 meters, 9.8 meters, 11.8 meters, 13.8 meters, 15.8 meters, 17.8 meters. And to find potential energy, we use this formula right here. Potential energy equals the mass of the ball times g times height. To find the mass of the ball, we used the scale in Mr. Cavanaugh's room, and the ball we found was 0.1935 kilograms. So we plugged that in for MB. Then we plugged in 9.81 for G, and then we plugged in the various heights of 1.8, 3.8, and so on. This is the one for 1.8, 3.8, 5.8, yada yada. And we found it to be, potential energy is measured in joules. So that is how we found potential energy for all of these. And now Logan is going to explain how we found this column, acceleration, kinetic energy, right here.
Okay, to find kinetic energy, it's based on acceleration since it's the energy of motion. So we use the KE formula, which is mass of the ball times velocity squared. And in order to find the velocity squared, we use the VF squared equation from Mr. Cavanaugh's study guide, which is VF squared equals 2 times the acceleration times displacement plus the initial velocity squared. And so we did all that times the mass and got 3.42, etc., which is the same as the potential energy. And they come out to be the same because the energy at the beginning when you drop the ball is the same as at the end. And now Melissa's going to tell you about our graph and independent, dependent variables.
Are you going to? Okay, well, the point of the lab was to measure different heights and to determine the energy. So our independent variables are acceleration, weight, and mass, which made our dependent changing variable height. And since the potential and kinetic energy were the same numbers, the graph will be directly proportional and was measured. The x-axis is potential energy, and then the y-axis was kinetic energy, which makes the slope 1 in our equation. Kinetic energy equals potential energy, which is measured in joules.
And now we're going to demonstrate our process.
Well, first we have to measure the height of Melissa's arm. We started out with 18 centimeters, which is also 1.8 meters. So Melissa, if you'd like to look over here. Now we're starting down here at
There's the dog.
18 centimeters is right here.
Good job.
Yeah. There, you just witnessed potential and kinetic energy. Now we will do 38 centimeters, which is 3.8 meters. There, again, you just witnessed potential and kinetic energy. Now we will do 58 centimeters. Notice how the energy when we start and the energy when we finish is the same. Now we will do 78 centimeters. Well done. Now we will do 98 centimeters. Notice how each time the height and the acceleration increases, just like our potential and kinetic energy did as the height increased. Now we will do 118 centimeters.
Okay.
Now we will do 138 centimeters, which is 13.8 meters. Notice our potential and kinetic energy looks the same. Now we would do 158 centimeters. Now we will do 178 centimeters.
Oh.
That one hit my finger. So therefore, the potential and kinetic energy was thrown off. Well, the potential was the same, but the kinetic energy ended up being thrown off due to my finger. Now we will do that again to just demonstrate it the right way. There. That is how we use mechanical energy to find potential energy and kinetic energy through the demonstration of dropping a ball. These are the formulas we use. This is just a common, everyday formula for potential energy, which is the force of the hand times the height. You can see we use that because the force of the hand is 9.81, as we have learned in Mr. Kavanaugh's class. So you plug this equation in, but now that we have the factor of the mass of the ball included in the equation, we also included that. Now,
when measuring kinetic energy, it's always going to be turned into something. It's never going to not exist. So it's going to go through a work process, and that's when thermal energy comes into play. But we did not show that, so.
stop it. I think you hit it again.